Welcome back. So the current tutorial is going to be related to the bisection of lines and angles. We're going to continue our introduction to propositions from book 1 of the Elements. And in this tutorial, we're going to work with two constructions related to bisection. The first will allow us to accurately divide an angle into two equal halves. And the second will allow us to divide a line segment into two equal halves. Both are going to rely on our ability to construct the equilateral triangle from a given line segment. So if you're not fully familiar with that construction yet, it would be worth pausing the video now and going back and reviewing that, because it'll be the fundamental skill that we need for these constructions. So I'm going to begin with Euclid's 9th proposition from book 1. Which is to bisect a given rectilineal angle So we're going to I'll draw it, but we're going to let angle BAC be the given angle. It might look something like this. Now what we're going to do is arbitrarily pick a point D on this leg of the angle, on the AB leg of the angle. And we're going to set our compass equal to the length of segment AD now. And we're going to transfer that length onto segment AC starting at point A. Okay, and that's just a result of our ability to cut a given segment from another longer given segment. Okay. Once we've done that, we'll label that point E. And this is where we're going to construct an equilateral triangle. We will construct an equilateral triangle. Put this aside for a moment. From this new segment, ED. And that'll just follow the construction steps that we learned in proposition 1. Set our compass to the length of ED. And there's our equilateral triangle. Now how this helps us to bisect an angle is that if we connect the vertex of the angle A to this new point here, let's call it F, then that new line segment is going to bisect our angle BAC into these two equal angles, BAF and CAF. So that's the result of the construction. We claim that those angles are equal. So why is that? Well, it all has to do with the fact that this triangle, DEF, is equilateral. So let's see what that gives us. Well, this side and this side, DF and EF, those have to be equal or congruent to each other because they're sides of the same equilateral triangle. These two sides, AD and AE, those were equal to each other because we cut those segments so they would both be the same length. And then finally, this segment here, AF, that's a side that's common to triangles ADF and AEF. It's common to those two triangles. So I've got two triangles with three pairs of corresponding sides that are equal. So I can conclude by the side-side-side relationship that those two triangles are equal to each other. And if the triangles are equal to each other, all of their corresponding parts are equal to each other. In particular, we can conclude that those two angles, angles CAF and BAF, which are corresponding angles of two congruent triangles, they've got to be equal to each other. And if they're equal to each other, that means that they are the bisected halves of this given angle that we started with. So that's why that construction works. I've lost my page, maybe. So why is it important? Well, a big application of wanting to be able to bisect an angle, it comes up when you are building mitered frames, maybe in casework. So if you're making a picture frame or a face frame for some sort of a cabinet and you want to miter the ends of the joints, you'll often have maybe two pieces of wood coming together with a mitered corner. And they don't have to be pieces of wood that are being joined at a 90-degree angle. Different frames might meet at different angles. But what's common to these two situations is that this angle is bisected into two equal angles right there. There and there. Or this angle is bisected into two equal angles there. And that's what happens with a miter joint. Well, another common geometric object that we might want to bisect is a line segment. And so that's the subject of Euclid's proposition 10 from book 1, which states we would like to bisect a given finite straight line. Running out of chalk. Not a bad idea to reload the chalk before filming. Well, anyway, so the subject of Euclid's next proposition, proposition 10 from book 1, is to bisect a given finite straight line. So we can start with some given finite straight line. Maybe we'll call it AB. So I'm going to do this construction in a way, Euclid's way, that lends itself well to being something that we can prove. But then when it's completed, we're going to go back, and we do this with many of our constructions, we're going to go back and see how we can streamline it so that we've got an efficient way of marking just what we need in our geometric figures to make this construction work. So anyway, if I'm going to bisect a given finite straight line, I'm going to call upon proposition 1 once again. I'm going to construct an equilateral triangle on this segment AB. And so I go through the same process. I set my compass to the length of AB, swing a couple of arcs, same distance from A as they are from B, to mark an intersection. I'm going to draw my equilateral triangle. I guess we might as well call that point C. The third vertex of that triangle, we'll let that be C. Well then, the next step of this construction is that we're going to bisect this angle ACB using the last construction that we just learned, proposition 9 from book 10. And so what that would tell us to do is to pick any point along one of the legs of the angle, right? And mark the distance from the vertex to that point, and then mark the same equal distance from the vertex to a point on the other leg. But since we know this is an equilateral triangle, we might as well just choose points A and B to be our arbitrary points, because we know they're already the same distance from C, because these legs have to be the same length. So I'm going to do that. I'm just going to set my compass to the length of AC. You know, it's going to work, but I'll double check that it matches up with AB. And then, remember what our construction for bisecting an angle told us to do. We would take those points and draw another equilateral triangle. Or find the vertex of another equilateral triangle anyway. And that vertex is the one that you would draw your bisecting line through. This is the line that's going to bisect angle ACB. And I'll go ahead and draw the other sides of this triangle just because it's going to help us with proving that this construction works. Okay, and so the question might be, well, why did I want to bisect the angle when what I'm really trying to do is bisect this line segment? Well, and what I'd claim is that that's what I've just done, because this ray that bisects angle ACB also intersects this line segment AB right at its middle. So let's make this D, make this E, and I'm going to argue that I've bisected AB by dividing it into two equal segments, AE and BE. Those two segments are equal to each other. All right, well, why? You know, why should that be true? And it's really going to boil down to calling upon one of our triangle congruence relationships again. So I would like to show that that segment is equal to that segment. Well, one way I can do that is to say by construction, those two sides are equal. AC and BC are equal because they're sides of an equilateral triangle. This side, CE, that's a common side to these two triangles, ACE and BCE. It's a common side to those two triangles. And then, since we've bisected angle ACB into two equal halves, those two angles, angle ACE and BCE, have to be equal to one another. So I look at this and say, well, look, I've got a side, an angle, and a side in one triangle that's congruent to a corresponding side, an angle, and a side in the other triangle. And that angle is contained between the two pairs of sides. So by side, angle, side, this triangle ACE has to equal this triangle BCE. And if the triangles are congruent, all of their corresponding components are congruent. In particular, those two sides, AE and BE, are corresponding sides of those two now congruent triangles. So we know they have to be congruent as well. So since AE and BE are now equal to each other, we know we've bisected line segment AB. Now, as I said, in doing that construction, we've drawn a lot of extra lines and arcs and things that really aren't necessary to bisect a line. They were necessary for us to see why our proof was going to be working, but most of the time when we are performing this construction in practice, especially in a design context, we're not going to want to draw all of these auxiliary lines. We just want to locate this point that bisects the line segment. So let's start over and look at the streamlined version of this construction that basically follows the same steps. We just are going to draw this. So here's our line segment A, B. That's my shop dog exploring. He doesn't want to stay on his bed today. So I'm going to set my compass to the distance from A to B. And from A, I'm going to swing an arc above AB and another one below it, roughly in the middle. From B, I'm going to swing the same sized arc so that it intersects the one above AB, and then another one so that it intersects the arc below AB. So I get an intersection here and an intersection here. Okay, so what are those arcs? Just so that we can relate them back to the original version of this construction. This intersection of arcs up here, that was what we did in our original construction to form the vertex of our first equilateral triangle. This intersection of arcs also formed the vertex of an equilateral triangle, but it was the vertex we drew the angle bisecting line through. And so, remember that angle bisecting line that connected this point to this point is the one that intersected my segment at its midpoint. So I can just go ahead and do that. I can put my straight edge on those two intersections, and I don't even really need to draw the full line. I just need to draw a little mark in here that forms the midpoint of AB. And that's all there is to my construction. So if I'm trying to do that construction quickly without making a bunch of other dark marks that are going to clutter up a geometric diagram or a design, that's a good way to do it. Now, there's some extensions of this construction that are worth knowing. If I wanted to design, excuse me, if I wanted to divide a segment into more pieces, I could continue to apply this subdivision construction to A to the midpoint and B to the midpoint. And that would let me divide this segment into halves. And then I could take each of those, or into quarters. I could take each of those quarters and subdivide them, and then I would have divided my piece into 8 equal pieces. So if I wanted to divide a line segment into 2, 4, 8, 16, 32 equal pieces and so on, I could just repeatedly apply this construction to each of the divisions that I've made so far. Later on, we'll learn a construction that will allow us to divide a line segment into an equal set of pieces of some other given number, something like 5 or 7 pieces. And that's just going to require some other skills that we haven't built up quite yet. In particular, we'll need to be able to copy angles and draw parallel lines. But we're making a step towards that, really, which ends up being a fundamental skill of dividing a length into some given number of equal pieces. If we can do that, that's going to be the critical technique that we need in order to start developing rational relationships between the sizes of different components in our design. If you think back to our very first tutorial and design workshop, we designed a stool that fit into a rectangular bounding box that was 3 units wide to 2 units high. And so I needed to be able to divide that box into 3 units wide and 2 high. So we're making a step towards being able to do something like that. And so in our next video, we're going to finally develop techniques for laying out perpendicular lines and hence right angles. Also a critical skill for laying out those kinds of rectangular bounding boxes.